Have you ever paused at sunrise or sunset, mesmerized by the deep red glow of the sun? Let's uncover the physics behind this natural painting. At these times, sunlight has to travel the longest distance through the atmosphere. Along the way, the shorter blue wavelengths get scattered out in all directions. By the time the rays reach our eyes, most of the blue is lost. What remains is the longer wavelength red light, which scatters very little. So the sky paints the sun red not because the sun changes color, but because our atmosphere acts like a natural filter. Pretty poetic, isn't it? Now let's fast forward to noon. The sun is right above us, and the light travels only a short distance through the atmosphere. Here, scattering has very little effect. Most of the wavelengths come together almost equally. The result? We see a whitish, slightly pale sky. Think of it like having all the colors of the rainbow blended into one. The atmosphere at noon just hands us back white sunlight almost intact. Here's the big question: why is the sky blue and not violet, even though violet scatters the most? When sunlight interacts with air molecules, shorter wavelengths scatter much more. According to Rayleigh's law, scattering intensity is proportional to 1 over wavelength to the power 4. That's why violet and blue scatter strongly. But our eyes are more sensitive to blue than to violet, so the sky appears blue. The scattered blue light from every direction fills the dome of the sky, nature's very own giant screen. Now imagine removing the atmosphere altogether. What would happen? No air, no scattering. Sunlight would travel straight, and there would be no diffused light to brighten the sky. The background would look pitch black. That's exactly what astronauts see from space, or what you'd observe standing on the moon, a bright sun shining in a completely dark sky. Meanwhile, Earth looks blue from space because of scattering, truly a contrast worth imagining. Clouds are another fascinating canvas of scattering. Unlike air molecules, cloud particles, tiny droplets of water and dust, are much larger than the wavelength of visible light. In this case, all wavelengths scatter equally without preference. When every color mixes equally, we perceive white. That's why fluffy clouds look brilliantly white on a clear day. And when they thicken, less light passes through, so they appear gray. So clouds are like giant projectors scattering sunlight in all directions, gifting us those breathtaking views. Now let's move from nature to technology. Why do traffic lights and railway signals use red? The secret lies in wavelength. Red light, with the longest wavelength in the visible range, scatters the least in the atmosphere. It penetrates farther without weakening. That means drivers can see red lights from the greatest distance. It's not just tradition, it's physics keeping us safe on the roads and railways. Next time you stop at a red light, remember you're looking at science in action.
Let's do a quick calculation to prove why red light travels farther than blue. Take the wavelength for red as 8,000 angstroms and for blue as 4,000 angstroms. According to Rayleigh's law, scattering is proportional to 1 divided by wavelength raised to the power 4. So the ratio of scattering of blue to red is 8,000 divided by 4,000 raised to the power 4. That comes out to 16. This means blue light scatters 16 times more than red light. That's the numerical proof of why red is chosen for danger signals. It travels farther, while blue scatters away quickly into the sky. Let's wrap this up with a recap. At sunrise and sunset, the sun looks red because blue is scattered away. At noon, less scattering makes the sky whitish. The sky looks blue because shorter wavelengths scatter more and our eyes pick blue best. Without atmosphere, the sky would be black. Clouds look white because big particles scatter all colors equally. And red light is used for danger signals because it scatters least and travels farthest. Scattering is more than just physics. it's nature's artist, painting skies, sunsets, and clouds, while also guiding engineers in choosing the safest light for signals. How amazing is that?